Okay, so my plan for this lecture is I'm going to give another construction for loss of regularity, and I'll probably finish a little early, and I will spend the rest of the time on the board just introducing what I will talk about tomorrow, which is an application of enhanced anticipation by using a resolve and estimate with application to the Kuramoto-Sibashinsky equation. And I want to, for the student who especially to discuss a little bit about this equation, because in my opinion, it's been overlooked in the literature. So there are a lot of interesting questions. I will explain. Okay, but okay. First, I will present you this other construction of loss regularity, and remember that it was motivated by this idea that we would like to prove loss of regularity for a vector field that has subordinate regularity, but for all classes that don't embed in the Lipschitz class, for all spaces, and also whether we can make some kind of universal construction. And the problem in the construction that I presented this morning is that the scaling is unfavorable the moment that R is greater than 1. So unfortunately, the normal view will grow also. Okay, so you don't get. But you can do a different construction that give you a partial answer to these two questions without appealing to mixing flows. And the key idea is that the blow-up of the positive norm is a local phenomenon. So the growth can be achieved with very simple flow that are not mixing. And so in some sense that allows to give an explicit computation of the growth of norm in time. And that is a more flexible, and so there is a more flexible rescaling here that you can do. And this is joint work with the Gianluca, Gautam, and Tarek that appeared last year. And this says the following. So you give me any locally H1 function in RD, so d greater or equal than 2, no constant, so non-trivial. Then we can construct a compactly supported divergence vector field, which is uniformly in time in WRP for any R and P that don't embed in the Lipschitz class. So P can be anything between 1 and infinity, not infinity. And then R can be greater than 1, but of course less than d over P plus 1. Okay, so we are not in the Lipschitz class. Such that the unique weak solution of the transport equation with velocity u and initial condition delta naught satisfy the property that instantaneously you come outside of the H1. So it's an ill-positiveness in H1, okay? You start out in H1 and immediately you're not in H1. And because our flow is actually smooth in space, if you start out in HS for S greater than 1, you also, of course, come out of HS. What we can't do with this construction is that we cannot control the fractional norms. And the reason is because the growth of the H1 norm is done by an explicit NHS here. So we don't know how to do it in HS. But Gautam pointed out to me this morning, and he is correct, that if I don't insist in loss of higher norm, I can use any exponential Lipschitz mixer that is universal, like one by John author, and then that should also work for the fractional. But okay, but it's Lipschitz, so you will control it easily each one. Okay, but I will still present this construction because the flow is so simple that it's really some sense. So we'll do everything by hand, okay? Everything will be explicit, okay? So the proof, a few comments before I give you the proof. So, okay. I think that this computer does not like me. This must be a Windows computer, I think. Doesn't like me. Okay, so the proof is still based on a rescaling of a basic element. But there is a delicate issue in the end of the construction that remember that we took cubes and we scaled them and we had the cubes accumulate at a point. In the previous construction, we could take the cubes wherever we wanted. Okay, so we can place them everywhere. Okay, here the location of the cubes where we do the rescaling We cannot choose it as we want. It is based on looking at where the H1 norm of the initial condition is large. So there will be a covering argument at the end, which is based on this fact here. And the basic element is constructed from the following observation, that the H1 norm of a non-constant function psi on the torus increased by a fixed amount under the action of a shear flow, which is parallel to the axis at time 1. So basic flow are just, again, shear. Okay, so shear flows appearing all over the places. And let me say that recently, okay, some results with have some flavor of what I will present, were done by Diego Cordova and collaborators for actually active scalar equation. So in 2022, Diego, Martinez, Zoro, and Wojtek Różański proved that there is loss of some regularity. It's not instantaneous, and it's only some regularity, but to have loss of some regularity is Souther spaces. So this is not a Holder space, it's a Souther space. For the 2D Euler equation in vorticity form. And the idea is in some sense very similar to ours. So you have some kind of norm inflation, okay, and then you do some rescaling, okay, to have loss of regularity, okay, shorter and shorter time. And the initial condition there works like this, okay, so they have a sequence of initial conditions, okay, and then they take a limit. And the construction is this, so they take, guess what, okay, a radial flow, not a radial, I mean a circular symmetric flow, okay, where things are very much controlled, okay, but then they add angular perturbations, okay, of higher and higher frequency, okay, so that's what's the initial condition, and then it's sequenced. And so when you look, and then they have a related construction. I haven't quite looked at this paper carefully, so I'm just going to mention it. It's 2023, where they look at 2D surface quasi-geostrophic equation, but with some fractional dissipation. And let me say that 2D Euler and implicit SQG are both active scalar equations. That is, there's a feedback of the velocity. Velocity depends on the scalar that you are transporting, okay? And let me say that when you look at the active scalar equation, some things are better than the linear and some things are worse. So the good thing is that the non-linearity will help with the growth of the norm, of course. But on the other hand, as I mentioned this morning, the superposition is very tricky, okay? Because the equation is non-linear, okay? So you have to control what happens when you start to add things. But I wanted to mention this. So instead our calculation, our construction will be in some sense much simpler because it's a linear equation. And this observation, okay, in 3 that the norm of the initial condition grows under the action of the shear flow, it's really an explicit computation. So for the students, I would try to do all the computations as explicitly as possible. So let me start with the notation, okay? So I will use shear flows. So I want to denote the profile by Fi of Z. So there will be 2 profiles. It's a sign profile, it's a shifted sign profile, okay? And then I will also use this notation for the elements of the standard basis. Okay, so EK is the standard elements of the standard basis, okay? So, so the growth of the norm will be contained in this lemma. So I start out by fixing some region of the torus. Let me call it omega naught. This is C1 subdomain. And then given any non-constant function psi in H1 of the torus, there exists a vector field which depends on psi localized to this subdomain here, such that if you use a shear flow, okay, given like this, I take one of these 2 sign profiles, shifted sign profiles, okay, that acts in a certain direction, and the direction is determined like this. So sorry, this should be a prime, okay? So if I fix J in Xj here, the prime here is exactly J plus 1 if I look at direction except the last one, and then on the last one I go back to the first one. Okay, so it's sort of as a cyclic. So in some sense, the shear flows actually in one coordinate, but to make it a shear, right, the direction of the velocity it's in another direction. Okay, so think that there is a J prime here, lost in the iPad. Okay, so this will be my shear flow. Okay, and so what happens is that the weak solution of the transfer equation with this shear flow, okay, starting from this function psi, has the following property, that for any fixed time t, for us capital T will be 1, okay, the L2 norm of the gradient of phi, so the H1 norm, okay, it's bounded below, okay, by the H1 norm of the initial, sorry, this is not the mean, it should be psi, okay, so the L1 norm of the gradient of the initial condition times a prefactor, which you see depends only on the property of the flow. Okay, so capital A is the amplitude here, okay, and that's it. Okay, so it depends on the amplitude of the flow, on capital T, of course, and on the dimension. So if you fix capital T and you fix the dimension and you fix the amplitude, that's a constant factor, and it's obviously greater than 1 because you won't grow. Okay, so here omega t is the image of omega naught under the flow. Okay, so we want to prove this lemma. So it's an explicit calculation. Okay, so we have we will introduce first. Okay, these flows here. Okay, so that depends on three indices. I prime and J. So I and I prime is one of these choices of the shifted shear sign profile, and J is the direction. Okay, and for each of those, you define a velocity, which is this shear flow here. Okay, and then let's go find the transport of the initial conditions by this shear, which you can write down explicitly, right? Because I mean, being a shear, you can write down the transport explicitly, and there is a missing T here also. Of course, it depends on time. So this will be the image at time 1, right? Okay, so, and then we are basically done, okay? Because once you do this, okay, my shear flow is a composition of these things, okay? And I can differentiate everything explicitly. I mean, I have an explicit form for the solution. So if I explicitly compute the gradient, okay, and then I sum over I prime and J, I have that the gradient of the sum of the gradient square, okay, it's exactly equal to the certain number of copies of the L2 square, the gradient of sine L2 square. And then you conclude by observing that there are at least 40 terms on the left, and so at least, and the right-hand side is a prefactor which is strictly greater than 40. So, you know, pigeonhole principle, one of these has to contribute to more than 1/40, and that gives the result. So it's really very simple, explicit calculation, and I have to thank the Automan Direct for noticing that, and I was really there doing. Okay, and then after that, it's a rescaling argument. And sometimes after that, we proceed very, very similar, but not exactly to what we did before. Okay, so first of all, once we have, of course, that we have growth, and you know, by fixed amount at each fixed interval of time, then we get exponential growth of the H1 norm. Okay, so first of all, using the lemma, given any theta naught in H1 log, we can construct a smooth in X, compactly supported divergence vector field such that the H1 norm of theta grows exponentially in time. So this is the first step of the construction that we did before. We first grow the norm exponentially in time, and then we do a rescaling argument to make them blow up instantaneously. So the first step is to have the exponential growth of the H1 norm, okay? And so once we do this step, which I will describe, then this flow and the weak solution it generates will be the initial elements of an iterative rescaling scheme, okay? And to construct this basic elements that gives exponential growth of the norm, we need to lift the flow with velocity u from the torus to RD. So our construction here is a construction on the torus. Okay. So how we do that? Okay, so I will describe the lifting only in 2 dimensions, but you can see what's easily that can be extended to any dimension. So first of all, let me identify the torus, okay, with a square of size 8, okay? And then I will choose omega naught to be the unit square inside here. Okay, so it's this little square here. Now the point is that by the lemma, okay, the vertical or horizontal shear will grow the H1 norm of theta naught. Say that we take a vertical shear. Then you look at the image of this little square under this vertical shear, and you can see that it's going to lie in this vertical strip here. Okay, so I call it S1. So the image at time capital T, say time 1, in fact, here, time 1, okay, the image will be somewhere in the strip here. So it will be square in the strip. And the idea is now that to embed this into R2, okay, I will deform this strip into an annulus somehow. Okay, it's a closed track that looks like this, and I can do it by keeping omega naught fixed. So this I can fix, and then I deform the rest. Okay, and because my flows are all smooth and you know, I can control the deformation here so that I keep under control the norms of the resulting velocity. So the resulting velocity will still be under control, even under this deformation here. And in fact, C1 will be under control. And why do we do that? Well, because this image, okay, of the initial square at time 1, think that capital T is time 1, okay, is somewhere in here. And by a rotation, I can always arrange that, in fact, that this is the last square. So in other words, once I deform it, okay, the image of omega 0 at time 1 is in fact also on top of omega 0, okay? So if I do this, I can ignore what happens over here, okay? Because I'm only interested in what happens at time 1. So then I have taken my construction and now it lives on the unit square in R2, okay? That's what happens, okay? So now we have lifted things on R2, compactly supported, and now we want to do a rescaling to make things grow. But first of all, this construction only tells me that at time 1, okay, I have grown the H1 norm by a fixed amount. So of course at time 2, I've grown it by double, at time 3 and so on. So how do I get exponential growth for all times? So this is the proposition that I want to prove. Okay, so now I have an initial condition in H1 log, okay? I fix alpha positive, and then there exists a constant which depends on alpha and the dimension, but it's independent of theta naught. That's important. And a vector field V, which is obtained by deforming the vector fields on the torus, as I explained in the previous slides, divergence free, supported on a certain cube. Okay, I have to take, of course, a larger cube. So I want the action field, a unit cube. I have to put it inside a larger cube, such that, first of all, the C1 norm of this vector field is under control. And you can think that, in fact, even the higher norms be under control. We just look at the C1 norm because we just are interested in showing growth of the H1 norm here. And the weak solution theta of the transport equation with velocity v and initial condition theta naught grows exponentially. So first of all, at integer time, you have exponential growth, and that's with any rate alpha that you've chosen. This follows immediately from the previous construction. And in between, you still have exponential growth, but okay, you lose a little bit because simply we interpolate. Okay, so we have exponential growth, but not at the rate alpha, but at alpha minus something. Okay, but that's still good enough to prove the blow up. So the sketch of the proof is simple. First of all, we lift the flow capital U from the torus to the space in the way that I described, and let's call V the resulting flow. Okay. So this V will live in this cube here, because once I take this strip and I deform it, actually this lives on the cube of size, on the rectangle of size 3, 4. Okay. So, okay, so once I lift it, let's see the action of these flows. First of all, if I compose the flow with itself at integer time, I immediately get exponential growth of the H1 norm at times that are multiple of that are integers, okay? And then I observe that because the C1 norm, particularly the Lipschitz norm of V, is uniformly controlled, then you can get the lower bound and intermediate times up to a small loss just by interpolation. Okay, so it's very, very simple. So now I have my basic elements constructed. Okay, so I know that I have a good flow, a good solution, okay, where the H1 norm grows exponentially. Okay, so how do I speed it up to make the blow up instantaneous? And that's where things are a little bit trickier than we first anticipated, okay? So we want to scale and iterate exactly as before. So let theta be the weak solution. Well, maybe I should have called it rho instead of theta. Let's call rho the weak solution associated to V, and this I will use as my initial block for the iteration. So now I want to pick a sequence of cube Qn with center Cn and side length lambda n. It's got lost lambda n with the following properties. Okay, so first of all, I want that if I make the cube a little bit larger, say by a factor of 7, these are pairwise disjoint, and they cluster to a point y. Okay, at this point y will be the place where the construction is not smooth. Okay, now the precise location is to be chosen later. And then up to a rigid motion, I will repeat. Happens to my slides. So. Right. There's something happened to my slide, but okay, never mind. Okay, so up to a rigid motion, I will repeat the construction I did on Q0 on the cubes Qn. So let's call Vn. This V restricted to Qn, okay? And I know that Vn grows the norm of theta of the initial data exponentially. And then I will define U and theta again by superposing this construction, okay? Now, the point is that, you know, I only have exponential growth at this point. I don't have blow up. So what I want to do is I really want to scale this Vn on the cubes Qn. And so I will not use Vn, which is simply V moved onto the cube Qn. I really wanted to rescale. Okay, so this is what really will give me my growth. So Un here will be a rescaled version of V, okay, by a factor lambda n in time and a factor tau n in space. And so if I do that, then my UN supporting Qn, they're smooth, and the entire U will smooth outside of a point. Okay. So what I can say about this UN and this theta n is as follows. Okay. That the WRP norm of UN will grow like this, okay, and will be, bounded by this quantity here, and the gradient of theta n will grow exponentially, okay, because they come from V and V grows exponentially. Now, the point is that we now want to choose our parameter so that the first inequality here is still bounded and the second one will actually become infinite. So in other words, at any positive time, I don't have exponential growth, I really have instantaneous blow up. So how do I do that? Well, what are my parameters? So my parameters are the rescaling of space, the rescaling of time, and the location of the cube. okay? So the cubes here are not arbitrarily chosen, but they will be chosen in such a way that I achieve these two things. And so I want to choose Cn and lambda n and theta n, so that I have still a finite norm here, but I have infinite norm here. And this is done by covariant lemma. Okay, so let me first tell you how I choose the location of the cube Qn and the side length lambda n, and then I will show you how to choose the time scale tau n. So the choice of the cube is done by covariant lemma. So I will choose the cube Qn based on where I will scale the local version of the H1 norm of the initial condition is large. So I cannot choose them as I wish, but I'm forced to choose them based on where H1 norm of theta 0 is large. And that makes sense, right? Because if I place the cube when the norm is large, then I'm jump starting the process, okay? And the way that I do this covariant lemma is as follows, okay? Let me call fx the L2, the modulus of the gradient of theta 0, the initial condition square, okay? And of course, since theta naught is in H1, f it's L1 log, okay? And it's not 0 because not identically 0 because theta naught is not identically 0. And then I define the following quantity. So I will denote by QR the cube center QRX, the cube center at X of side length proportional to R. And AR is a maximum is the average of F over the cube QR. Okay. So I will do some kind of maximum function argument in some sense. And so given the function R, I look at the following. First of all, I define the set D tilde to be all the point in X, where when I take R to 0 in this expression here, I get back f of X. So by the Lebesgue differentiation theorem, we know that T tilde is full measure, right? Because f is locally in L1. So that says that if I fix a tolerance delta bar, so a delta bar, a positive number delta bar, since f is not identically 0, the following must also happen. That there exists a subset of positive measure of this d tilde, I will call it d, where not only I know that I converges to f of x, but I know that the limit is not 0. So the limit is bounded away from 0 and is bounded away precisely by this tolerant delta bar. Okay, now I have to intersect to a ball because f is only locally in L1. Okay, remember that everything will happen on a compact support, so I can ignore what happens at infinity. Okay, so on a ball, okay, I look at places where this average converges back to f of x and is strictly positive, but bounded away from 0. Okay, so then that's how I will choose my my center and my side lengths. For any point x in D, I know because of this property here and this property here that there exists side length r of x, okay, such that the integral of f of x over the cube qr for any r less than rx is in fact at least half of delta bar, okay, times the size of the cube. Okay, so I control the average from below in terms of delta bar and then some quantities that depends on the image. Okay, so then that says that there exist countably many points and countably many lengths such that the following happens. So Mn, which is the L2 norm of the gradient of the initial conditions, it's on the cube, it's bounded below from by lambda n to the power t. Okay, and this lambda n, I can choose it to be exponentially decreasing because I have this property here. Okay, so I don't really know where these CNs are, but I know that they exist. Okay, so once I do this, then we are done. So, and also I can choose, because this as positive measure and d tilde as full measure, I can choose this center so that the cubes are well separated. So in other words, I can choose the Cn such that the cube of side length lambda n center at Cn has the property that the 7qn, so 7qn is the concentric cube of side lengths 7 lambda n are pairwise disjoint. So there was, and then I am in the home stretch because, so first of all, since D is bounded, since the ends are countably many, they have to accumulate at the point, okay? And that's exactly where the construction is not smooth. So again, this is one situation in which I can make the singular set just be a point as small as possible. And furthermore, because D is bounded, it also says that everything happens in a compact set. So I can make the union of this cube to be of finite volume. And lastly, I need to choose the rescaling in time, okay? And that is an explicit calculation. So first of all, so remember these two estimates here, okay? So I know exactly how to bound in terms of lambda n and tau n, the WRP norm of the n from above, and from below the norm of the gradient of theta n, okay? So then it's an explicit calculation. So first of all, so I will have that the H1 norm of theta is infinity if these two, if this first estimate B1 happens, okay? So because this is a lower bound on the H1 norm. So if this quantity here is infinity, then I'm done. So there is a missing infinity here. So this should be equal to infinity. But on the other hand, I want this to be controlled, and that again by this explicit estimate by rescaling, I have it in this series is finite. So I want this series to be infinite and this series to be finite, and I want it to be finite for every gamma, where gamma is exactly the Sobolev exponent, right? And so how do I do that? Well, lambda n and Cn are fixed, right? So I cannot change that. So the only thing I can change is tau n. So can I choose a tau n so that these two things are achieved? The answer is yes. So you take tau n to be the log of 1 over lambda n to the power minus 2. And then it turns out that you can verify the first estimate that this series is infinity. So there's a missing infinity here by direct calculations. But we also want this series to be finite. Is that the case? Well, then I need to do a splitting of the series into a low frequency part and a high frequency part, depending on this exponent gamma. So what I can show is that there exists an integer n depending on gamma, such that if n is above capital N, then the log is bounded below by this lambda n to the power minus gamma. And if that's the case, then you split the series into a low frequency part and a high frequency part, and you can control both of them. So the low frequency part you control directly by the log, and the high frequency part you control by lambda. That's the end. Okay. But again, a very simple construction. We just use shear flow to grow the norm, and then we scale. The only things that we didn't expect is that you had to do this covering arguments to control, to choose the cubes. So a couple of open problems. So can we modify this construction to show the loss of the fractional norms? Well, we don't know, and part of the problem is that before we use interpolation, okay, to control this, and if we want to use interpolation, this requires a lower bound on the negative norms. That is, we need to have a mix. Okay. And then maybe a more interesting question is, can we construct a universal explorer? The point is that the construction I just gave you, of course, the flow depends on the initial condition, but the construction is the same. The only dependence on the initial condition is where to put these cubes. So the idea, possible idea, but it's a delicate construction, is that if we replicate the construction I just gave you on a sufficiently dense set in LD, maybe we can make all norm explodes, okay? The problem is, of course, that now the cubes are no longer disjoint, and the moment that the cube interacts, you could actually have that they dampen each other. So you can't guarantee anymore that the growth on each of the cube will survive. Okay, so that's that. Okay, so the rest. So how much more time I have? So I will go to the.
15 minutes. Yeah.
Okay, perfect. So I want to devote the rest of the time just to discuss an equation, which I will address tomorrow using advanced dissipation. This is, for the reason that I explained before, I think it's a good problem for students. Well, a very open problem, not simple, okay? But I think it's an equation that has been a bit overlooked. So this is the Kuramoto-Sivashinsky equation. This is the model for a long wavelength instability. So you start to see that mixing will help here, right? Because if instability is a large scale, the mixing will move stuff to small scales. But the equation that is very interesting mix up. Okay, so it's interface dynamics. It was really derived by Kuramoto-Sivashinsky as from a coordinate-free model of interface dynamics in combustion. Okay, so it comes from combustion. Counter propagation in combustion. And part of the reason why this was overlooked in dimension is very much studied in one dimension, but it was overlooked in dimension greater than one, is because if you think that this is in interface dynamic, really the physical dimensions are d or 1 and 2, okay? And this is the, I'm gonna write the equation in a minute. This is a very well behaved equation 1D. It's like in some sense what Celine was saying today at the camera. Everything, almost everything in 1D, but you do almost nothing in 2D, okay? So what's this equation, okay? So there are two forms, okay? So there's a scalar form. Okay, so here the unknown is a scalar function, okay? Phi from okay, in fact, we start on the torus. Okay, let me say it's RB across infinity into R. Okay, and the equation look like this: dt phi. Okay, now I always messed up the sign. Okay, so it's plus phi Laplacian of phi plus Laplacian of phi. Okay, plus gradient of phi. The modulus gradient of phi squared equal to 0. Okay. No, this is not a mistake. The Laplacian has the wrong sign. That's where the long wavelength instability comes from. So this amplifies large scales. You have a biharmonic, so it's hyper-dissipative, okay? And then you have a concept, a nonlinearity, which is in conservation form, okay? And then there is a vector form. I want to write the vector form because it will look more familiar. So U here is the gradient of phi, okay? And then the equation look like this. Of course, the linear part is exactly the same. Linear. And then the nonlinearity becomes very familiar because it's Borgers. Okay? It's just Borgers. Use the fact that it's curve-free. Right? Okay? So in other words, so this is the hyper-dissipated Borgers with the Laplacian with the wrong sign. Okay? And we know almost nothing about this equation. So in other words, so of course, regularity is not an issue here. What the issue is the long time behavior of this solution. In fact, the long time existence. And let me say why 1D things. So there are still many interesting questions because even in 1D, this is a chaotic system. Okay, you have chaotic trajectories. And there is in fact a very interesting open question on the long time dynamics. It's conjecture that if you if you take random initial data, that's the dynamic is really captured by KPZ, okay, the Kasdan-Paris-Jean equation, but there are no rigorous results of that. It's 1D, but in 1D you do have global existence. The reason for that, okay, and there are different proofs. There's a proof by Tadmore, Ethan Tadmore, the 90s, I forgot exactly when. There's another proof by John. So at the same time, there are two different proofs, okay? But the Tadmore proof is an energy estimate because in 1D, okay, so the vector equation becomes EP plus UXX plus UX, okay, and then you have U dx, and this one is dx squared, okay. So when you take the integral of U, so if you try to do an energy and estimate, right? So if you try to control the L2 norm here, at some point you have to do U, okay, dx square, okay, dx, and that's also an exact derivative, okay. So this thing is U, okay, both in the periodic boundary condition. Yeah. Oh, sorry, you're still. It's ordering here to do that. Thank you. Yeah, absolutely. Okay. So you see, you have an energy estimate. So the L2 norm is under control, and you can prove that's easy to do, very easy to do, because it's hyperdissipative. The L2 norm is the norm that you have to control. If you control the L2 norm, you have both for U and for piles, in some sense, the H minus 1 norm of U, it's all you need to control, okay? And you get the global existence. But in dimension be greater than 1, dimension equal 2, we don't know how to control any norms, okay? In fact, I don't know of any conserved quantity or control quantity except the average, okay? So the average of, let's say you're on the torus, you take the average, just satisfy no DE. Okay, so if you can control the gradient, you control also the average, okay, and zero average is preserved. Okay, these are the only two things I know. Okay, and why is that? Well, because if you try to do an energy estimate in high dimension, you have to replace this by the integral of U dot gradient. Sorry, U. So gradient U, okay, this is not really different than the Navier-Stokes because U is not divergence, okay? And so L2 norms, you don't know what to do. But you say, okay, but this looks like burgers, okay? I mean, so in fact, let me do this. Let me take away this. I still don't know how to prove global existence. So this is hyperviscous burgers, and why? Because for Borges, you have exactly the same problem, okay? So Borges would be this equation with minus Laplace here, okay? So heat equation plus this nonlinearity here. With Borges, the way that we prove global existence to this system is not by energy as it is by maximum principle argument, okay? You control the energy norm. But the moment you have a bi-Laplacian, the maximum principle is out the window. And it's even worse than that, because you could say, well, I don't really need the maximum principle. I need an infinity estimate. But these nonlinearities are not positivity preserved. So I don't even know how to control if you say to prove that positive solution stay positive, okay? Because the equation, in fact, you don't know how to set that, not positivity preserved, okay? So even if I take hyperviscous burgers, I don't know how to prove global existence. Okay? So what can we prove? Okay.
Sorry.
Yes.
Hyperviscous burgers with
I don't know.
Existence.
Yes. No, you can prove global existence for small data. That you can do, but for large data, no. Oh, no, 1D is fine. Yeah.
Right.
No, I'm talking about 1D, everything is fine. Even Kuramoto is fine, okay? Higher D, yeah.
Sorry, my fault.
So what we can prove is that you can prove that if you take away the Laplacian, or okay, if you so let me say one thing that let's just work on the torus. So on the torus. Okay, and let me just say T equals, okay, because that's the physical dimension, the first one where we don't know how to do things, so D equal 2, so on the torus T2, okay, the linearized operator, okay, so let me call it L, okay, which is minus Laplacian square minus Laplacian, okay. This operator is multiplicative, okay, but it has large frequency, but it has growing modes, okay? So L has growing modes. Just do a Fourier series, okay? It's growing modes. Okay, so the torus, you really want to take it to be an anisotropic torus, okay? So it's a 10, okay? So L1 and L2 will be 2/3 as growing modes if Li is greater than 2 less. The moment that the one can greater than 1, okay? The moment that one of these two periods go above 2 pi, you have growing modes, okay? And you have one growing mode for each interval of 2 pi, okay, in each directions, okay? So if you take away the Laplacian, or okay, if the torus is small, okay, the periods are less than 2 pi, okay, so if line is that, okay, we have global existence for small data, and this is of course not done by doing an energy estimate, okay, but this is by minus solution. In other words, what you do is you integrate in time, okay, you use a semi-group generated by this L as an integrating factor, so you write down by Duhamel's formula an integral equation, and you solve that integral equation directly with 0 plus infinity in time in a certain space. You prove it's a contraction if the initial data is smaller, okay? And you can do that in many spaces. So this joint work I've done with David Ambrose, Drexel. So you can do it, okay, in L2, or you can do it the linear algebra. Linear algebra is nice because it works really well. Okay, but what about okay? But this is highly unsatisfactory, right? I mean, even without growing modes, I can only prove it for small data. So what you can do if you have growing modes, okay? Well, we can in fact, this is also joint work with David, we can in fact prove. Well, I could say that there are a few results in the literature on this equation in high dimensions, global existence, and it's for an isotropic domain. So in other words, if your domain looks like a one-dimensional domain, either because it's highly anisotropic or because it's thin, then yes, you can prove global existence, okay? So I should mention the work of Cell and collaborator. There's also work of Igor, Kavitsa and collaborator, okay, and so on, okay? But we wanted to do something where the side you don't take something close to one dimension, and then that is so if the domain is not thin, the domain is not isotropic, is close to isotropic. That's what we can do. Okay, so we can take small data plus one growing mode in each direction. Okay. So in other words, we can take L a little bit above 2 pi. Okay. Okay, and this is a Lyapunov function argument. Okay, so in other words, we look at the evolution of the growing modes as an ODE system, okay, and then we look at the remainder, okay, separately, and the remainder acts as a forcing on the ODE system, okay. But the reason why this has something to do with mixing is that we can add advection. Here. In other words, I will call this the advective Kuramotov-Sivashinsky. So Kuramotov-Sivashinsky is a mouthful, so I'm gonna just need to say KSC, and this will be AAC, okay, advective KSC. So it looks like this. So we do it at the level of the scalar equation, but you could do it for both of them. But, well, okay, no, I shouldn't say. You do it at the level of scalar equation because mixing of vectors is very complicated. So we just do it for phi, okay? And it looks like this. It's exactly the previous equation. This is phi. Okay, but now here we add v logarithm. Okay, important here. Okay, so we add an advection term by given vector field. And this is a physical model. Okay, so we wanted to look for modification of the equation that were physically motivated. So if you look at the combustion in premixed, okay, so in other words, you have combustion happening on something that is carried along by a background flow, then this is your equation. Okay, so this is physical equation. And if V is mixing, or if V is such that you have enhanced dissipation, okay, so tomorrow we'll discuss one case in which started with shear flow, and then I will also discuss radially symmetric, circular symmetric flows, then all of this restriction go away. So in other words, okay, so if this V is suitable, okay, to make the dissipation time as small as needed, okay, then we can take arbitrarily large initial data and we can take as many growing modes as we want, okay? So tomorrow I will discuss this, but I wanted to introduce this equation because there are some very basic open questions that, as I said, take hyperviscous burger and prove global existence with no restriction on the size of the data. I don't know how to do that. It should be true, okay? But this is an interesting equation, and tomorrow I will discuss it. Okay, so thank you very much.